now we are going to start with including forces that they are non-conservative. Now, the term non-conservative is applied to forces that don't satisfy the conditions of conservative forces that we discussed last time. Now, one of the things that I will say the most important characteristic is that we can't, I will say, reuse the energy. Like energy, we will say here, when we have a non-conservative force, energy is dissipated. Dissipated means it will be converted into forms that we can't use again. Now, mostly here I'm talking about friction, but there are other non-conservative forces that they're gonna add energy to the system. Okay, now for the friction, I need to include work done by friction in my conservation of energy, and that is going to be the force of friction times d cosine 180. And this is the reason why work by non-conservative here, in the case of work of friction, is going to be minus Fd times d. Now that F, K, which is the force of friction, it is, as you know, a mu K times the normal. Okay, mu K, we said, usually this is given, coefficient of kinetic friction, and normal, it is the normal force. Also, there are occasions where I have non-conservative forces, but these, they're gonna add energy to the system. These usually we're gonna say F times D. They're gonna add energy to the system based on, they are really doing positive work. Now, I will say this is the most general form of energy conservations. Is going to be the following. EI plus work by non-conservative should equals E final. And here, usually I do the following. As I said, I told you, like, I'm using charts. Then I will say this is my most general one, where I'm gonna have all my three types of energy. Then this is I, and this is final. K, this is Ki, this is K final. UG, it is UGI, UG final. US, it is USI and US final. And here, work by non-conservative is gonna be the force times d cosine theta in general. And then when I translate this is to an equation, this is how it's gonna look. And most of the time you're gonna have a lot of zeros here. We're gonna see how we're gonna apply this to different situations. Then here I will say EI is gonna be KI plus UGI plus USI plus force times D cosine theta, and this should equal K final plus UG final plus US final. I'm gonna show you now how we are going to solve several of these problems related to conservation of energy with all conservative, with non-conservative. I will see how we are going to deal with different situations. The first one, because I did not solve for springs, I'm gonna solve the first one, which is about springs. It takes 180 joules of work to compress a certain spring 0.15 meters. Usually this statement, it is used to calculate what is K. Now A, okay, what is, and this is the sequence of questions, what is the force constant of this spring? Now B, to compress the spring an additional 0.15 meters. Does it take 180 joules more than 180 joules or less than 180 joules? Verify your answer with a calculation. Now the first thing is I'm gonna use the work done, 1/2 kx squared, and I will say 180 joules. Like for me here, this is the spring, and I compress the spring, then my D is in this direction, and then this is 1/2 K negative because it's in that direction, but it's not very important here because it's gonna be squared, and then from that I will get K as 1.6 10 to the 4 newtons per meter. Now the second question is, I have my X as 0.15, and then it said if you want to have it, this is X1, double, like add in another like 150, which is going to be 0.3. I will say what is the work done is going to be 1/2 x2 squared minus 1/2 kx1 squared. This is how we're going to deal with it. And then it's going to be 1/2 k x2 squared minus x1 squared. And I will use, of course, my K, the one that I have calculated, and here negative 0.3 meters squared minus 0.15 meters squared, and this is gonna be 540 joules. Okay, because it is actually the formula is a square. It's not something that you are going to deal with just using, if you double you will it's something that is going to be a little bit different. All right, and now I will show you how I'm gonna use a friction here in that problems here. Okay. Okay, I'm gonna look at one of the problems that I wanna have it like more general than just having just friction. Okay, and let me see here. Okay, whenever we have conservation of energy, as I said, we might have it as that most general one, and then after that we will be able to do something like getting rid of some of the quantities, and that is where we are going to have it simplified. Let's assume here I have example here. I have a 60 kilogram skier with an initial speed of 12 meters per second, costs up a 2.5 meter high rise. Okay, kind of something like this. Now the angle here is 35. This is 2.5 meters. And what is really V final here? Okay. We want to find her speed, her final speed at the top. And we know that the coefficient of friction between her skis and the snow is 0.0800. Okay, and now here we will have, like always, you need to worry about yeah, this is here, we can make it like it's gonna be like I seem to be straight. What I was going to say, okay, yeah, I'm worried always about my initial and my final. Okay, the solution. When I will have that situation, I will make this here we don't have here any springs, and this is the reason why I will not have them in my table. Then here I final. Okay, I will say here this is my K in joules. Initially she had a velocity, and I'm looking for her velocity at the final position. Also UG in joules, I can use my UG here, 0, the reference, and then here is gonna have mg times h. Now, work done by non-conservative, I have the force of friction, then it's gonna be Fk times d, and d is gonna be the distance that she is gonna travel here. This is the one. Now, the first thing, like here we need to calculate more than one thing. The first thing is I want to calculate d, and that has to do with sine theta. It is the opposite, that it is h divided by d, and then my d is going to be h divided by sine theta. H is 2.5 meters, and I need to find what is sine 35. It is 0.574. Then I will say it is 2.5 divided by 0.574, and that is going to be 4.36 meters. Also, while she was moving here, she had, okay, I need to draw her free body diagram because I need to find the force of friction. This is she has the weight downward, and she had also the normal, and there is the frictional force here, Fk, while she was going up. Now, okay, based on my sigma F equals Fy equals 0, normal minus, and okay, yeah, now it's also, I need to find which one is 35, and of course this is 35. Normal minus mg cosine 35 should be 0, and you will find that the normal is going to be mg cosine 35, and that normal equals her mass, which is 60 kilograms, times 9.8 times cosine 35. Then I will calculate this number also. Okay, the normal force, it is 1.7 newtons. I can find the force of friction to be mu k times the normal, and mu k it is 0.0800 times the normal. Okay, then I will have that 0.8, and that is gonna be 385 in newtons. And then finally, work done by friction is going to be negative the 385 times D, which is 4.36. And that is gonna be negative 1680 joules. Okay, I can say now EI equals E final. Then initially her kinetic energy was 1/2 mvi squared plus her UG was 0, and the work done by non-conservative. Okay, here I forgot that term here. That equals 1/2 mv final squared plus mgy final. Here, remember, I told you sometimes you cannot drop the mass. And here, these are one of the situations. Then here I will say 1/2 times 60 kilograms times 12 meters per second, all squared minus 1680 should equal 1/2 times 60, and this is my unknown, plus 60 times 9.8. Y final is 2.5 meters. I want to collect, I want to calculate all my numbers here. Then this is 12 times 12 times 30, and that is gonna be 4,320 joules. And the other one, okay, here 30, and here 2.5 times 9.8 times 60. This is gonna be 1470 joules. Then finally, if I wish to calculate the solution, the V, I will say this is with a minus 1680 plus 4320. This is gonna be 1170 joules, should equal 30 kilograms times V final squared. Then I'm gonna divide this by 30, and I will not forget to take the square root. Then she will be moving with that velocity. Then here we have included friction. Okay, sometimes I will be interested not only in how much work is done, but how fast it is done. And this is where we are going to talk about power, which is energy per unit time. And then I will say I can calculate the power as E divided by T, and this is B joules per second, and joules per second is gonna be watts. I can say also it is the work done by T, and again it is watts. And I will say we can calculate the power for any machine. This idea is really more common when we talk about electricity and things that they operate with electricity. We can say E also equals PT, which is the energy that we are using for something that has a power of P. Now, we need to know that electricity bill is the numbers are stated in a unit. It is a unit of energy, not a unit of power, with kilowatt hour. And 1 kilowatt hour, it is 1 joule per second times 1 hour 3600 times 1000 because of the kilo, and 3600 it's because of the 1 hour, it is 3600. Then 1 kilowatt hour is 360000 joule, because joules are really very small. This is one of the reasons why we use kilowatts hour. Thank you, and see you soon.